notes. So my name is Sarah Asuna. I followed the master's program in AI here at the VU. And I will present on my thesis in which I studied the dynamics of epigenetic influence in insomnia. I studied this from a higher order modeling perspective, which follows an approach which was introduced by Professor Sir, who was also my supervisor for my thesis. And I want to start by thanking you for the supervision and thanking all of you for being here and for traveling all the way to Amsterdam, and also my family for being here, because I'm very grateful for all your support throughout my studies. And I'm excited to tell you about my thesis. The main aim of my thesis was to figure out if and how a computational model could be utilized to effectively simulate or model the influence of epigenetic processes in the development, persistence, and potential reversibility of insomnia disorder, also known as ID. And this entails that the model or the simulation should first show healthy functioning processes of a healthy individual, and then for an individual who has developed insomnia disorder, and later the functions when insomnia disorder is reversed, for example, through an epigenetic therapy in this case. I will first quickly give some background information on insomnia disorder and epigenetic processes, and the epigenetic factor that I believed was relevant to include in the model. Then I will briefly discuss the higher order modeling perspective. Well, Zoe has already explained a lot about it, so I will mostly focus on the functions that I used. And then I will present the network model that was created for insomnia, and present the simulations and discuss what these simulations entail and what the findings of this thesis are, what makes it relevant, and how it can be enhanced potentially for future research. And after that, I'm happy to answer any questions if there are any. Okay, so first, insomnia disorder. I see that I did not put my references in this slide, but this information comes from Palagini et al. 2014, Dulson et al. 2014, and Borges et al. 2024. But insomnia disorder is a prevalent stress-related sleep disorder. It affects at least 10% of the global adult population. It is a common factor and significant influencer in other psychiatric disorders, such as major depressive disorder, PTSD, and anxiety disorder. And it was found that therapy methods that are specifically designed for ID can not only alleviate the symptoms of ID, but also for other psychiatric disorders in patients that suffer from both conditions. An example of this is CBTY, that's cognitive behavioral therapy for insomnia. This adds relevance to a better understanding of ID, because the development of new therapies can potentially not only be beneficial for ID, but also for other psychiatric disorders. Okay, so ID has many different symptoms and characteristics. The most obvious ones are related to problems with sleep, but there are also a lot of problems related to emotion and mood that are also often visible in other psychiatric disorders. These include considerable distress, impairments in daytime functioning and cognition, heightened sensitivity to stressful events and negative memories. So, for example, they also respond in a highly sensitive manner to stress and negativity. And they also often display anxiety-like behavior. And then there are the problems related to sleep, which are mostly in the initiation and the maintenance of sleep, and dissatisfaction with the quality and duration of sleep. And this differs from normal people that have a bad night, because you're probably not always satisfied with your sleep or find it restorative. For example, when you have a thesis presentation the next morning and you have abnormal stress from it and you're nervous, then you will probably not sleep well that night. But as soon as your thesis presentation is over, you will resume a healthy pattern. ID patients do not have this. So even if the stressful context is gone, they will still have these problems with their sleep. and they persistently perceive their sleep as non-restorative. This has mostly to do with the fact that ID patients do not have restful REMs, but their REM sleep is fragmented. I will go in on REM sleep a bit more in the next slide. But for now, it's important to remember that fragmented REMs really disrupts the restorative function of sleep. And so why is it important to remember REM sleep? This has to do with two things mostly. The first is that REM sleep is one of the only objectively observable measures with which we can see if a person has insomnia or not. So through fMRI, you can observe brain activation patterns and REM sleep patterns in patients. And we see that ID patients have very significantly lower REM's duration and frequency. So their REM sleep is fragmented. And you can also see this as a disturbed brain plasticity stress-related response, because these REM's fragmentations also involve high sensitization of the amygdala, and this shows a disturbed stress response in the brain plasticity. The second reason why REMS is important is because it's a link between the two underlying mechanisms that I will focus on in the thesis. Of course, there are many different factors that can contribute to the risk of ID, but I focus on processes in emotion regulation and sleep-wake regulation, because it was found that disturbed processes in both of these regulation mechanisms can contribute to ID development. These findings are by Van Sommeren et al. Mostly. And emotion regulation, we saw a bit about it already in Zoe's presentation, but there are two brain regions that are mostly of importance here. That is the amygdala and the prefrontal cortex, PFC. So normally you will detect a stressor, for example, and you will feel this stress, and this can, you will sense it and you will make a representation of it, and you can feel this emotional distress or fear or arousal. And that feeling can be represented as activation of the amygdala. So for that, a state is also included in the network. And the prefrontal cortex, this will detect these high levels of emotional distress or arousal, and then it will function to suppress it. It will try to suppress this high activation of the amygdala and these high levels of emotional distress. And it will also suppress the high emotional response that would be provoked by it. So this is how emotion regulation works in a simplified manner. And this emotion regulation process was also inspired by Slur, 2016. And there's a sleep-wake regulation process. Sleep-wake regulation normally functions to facilitate a smooth alteration between the two states that you pass during a day, namely the state of wakefulness and sleep that lasts 16 to 8 hours respectively every day. It's quite a complicated process, but to simplify it, we can say that wakefulness is facilitated by the activity of wake-promoting neurons, and sleep is facilitated by the deactivation of these neurons and the activation of sleep-promoting neurons. And sleep needs a de-arousal process, and sleep has two phases, NREMs and REMs, so non-rapid eye movement sleep and rapid eye movement sleep. And REMs, which I mentioned, is the deepest sleeping stage, and this really needs this de-arousal. So levels of arousal should be very low or even absent to enter this deep sleep stage. And it's necessary because otherwise REM sleep will not be restful. And REMs needs to be restful because then it will aid in overnight adaptation. So it will help to neutralize emotional distress and reprocess negative memories. So in that sense, it also helps the emotional regulation process, but it also depends on the emotional regulation process, because arousal is highly associated with stress. So if you have high levels of stress, you will have high levels of arousal. And that's why REM sleep is important for this process of insomnia disorder. For these underlying mechanisms that I mentioned, there are states included in the network. We see that the amygdala is presented, or you don't see that, but I see that, but the amygdala is presented as the FSB state, the emotional response as a PSB state, and the prefrontal cortex as the PFC state. Then there's a state for REM sleep and a state for restorative sleep. That's the end state, and that is something that ID patients do not have. Then for the sleep-wake regulation, there are some extra states included, namely the sleep-deprived context. So that is a context state that simulates the natural tendency to want to sleep and wake up every 16 to 8 hours respectively, and this persists throughout all days of your life, mostly. And there is a state for stress reactivity and sleep reactivity. Sleep reactivity is the tendency to follow stress with a sleep disturbance, and stress reactivity is the tendency to follow disturbed sleep with a high emotional response. So after a bad night of sleep, you will act really stressed out. I can maybe quickly mention these other states as well. So there's a context state for normal stress. That's just everyday stress that's always present. And there's a context state for abnormal stress. So something that happened which was really bad. Like I said, I see my slide is a bit weird, but we are studying the influence of epigenetic processes. Zoe has already mentioned quite a lot about it, but to briefly state, it's cellular alterations that are caused by environmental factors, such as a stressor, that can cause changes in gene expression and function that can be very long lasting, but do not change the DNA sequence. So it's really nice to look at this because it could explain the long lasting effects of stress in the brain plasticity, which is in ID patients. It's also nice to look at because it's dynamic and reversible. So if ID is considered an epigenetic disorder, it could potentially be reversed with an epigenetic therapy. A study by Balakatire-san 2023 found that there's a microRNA miR221, which can be triggered by stress, and that stress or abnormal stress will cause an upregulation of the expression of this microRNA. And this will increase the gene coding for stepnin1. And that is associated with high fear responses and stress responses and a reduction of REM sleep. So that's exactly what we see in ID. So this microRNA in the BLA, that's the basolateral amygdala, really mediates the negative effects that stress has on sleep. And it's also seen that microinjections of an antagomer for this microRNA can block the upregulation of this expression and also reduce the negative effects that stress has on sleep. So that can be proposed as a potential epigenetic therapy. This is included in the model. So we already explained the formula for the model, but to briefly say something about it, it's a network model with multiple levels of networks, and all states in the network are connected to each other or have connections, and they have a value between 0 and 1. In the base level, the states can have causal impacts on other states and influence the value of those other states. And the states in the higher orders can influence certain attributions of the other states. The attribution that is used here is connectivity. So that relates to the connection rates between the states. That means that the strength with which one state impacts the other has been made adaptive, and this adaptivity is controlled by the states in the higher order. These are W states. Then there were multiple combination functions that could be used. I used 3, the advanced logistic sum. I use this for almost every state because it's great as you can set the parameters for sleepiness and excitability threshold. So the minimum value of the impact or of the other states to excite this change. Then I used the step 1s and the step 0 function. The step 1s I used for environmental factors that occur once. So the context of therapy and the context of abnormal stress, which will be introduced. And the step mods I have used for environmental factors or contexts that happen repeatedly, because it allows for repetition throughout the whole process. And this is used for the context of the sleep tribe, which I just described. And this is repeated every 16 and 8 hours. Okay. Then this is a representation of the network. I'm sorry, Sophie, but here we see the states for emotion regulation, so the PSP I mentioned, the PFC, the context for normal stress that happens every day, and the context for abnormal stress, which will increase the stress levels here and will trigger upregulation of the epigenetic influence. So the epigenetic influence is represented as these higher order W states. And the one in the 5th order shows the expression of the microRNA T21 that I mentioned. And this exudes control over the other states downward. And essentially it will influence the values and the adaptivity of these states. These W states regulate the connection weights for the FSB to the SLR. So that's how stress impacts sleep reactivity, and sleep reactivity is how you respond to stress in the sense of sleep disturbance or not. So there's a negative effect on REMs and a negative effect on restorative sleep. Then there's also an adaptive connection weight for the interaction between stress reactivity and sleep reactivity, which I discussed before. And in the highest order, you also see a context state for therapy, which has a negative effect on the expression of the microRNA, so it will reduce the expression. And this will also reduce all the values downward and reduce the impact of these connection weights that I mentioned here. Okay. So I simulated this process with the model, and this came out of it. I hope it's visible for you. So in this picture, you see that there's a repetition every time in this purple one. That's the context for sleep time. This happens throughout the entire process because it's repeated with the step-net function. And you see a normal emotion regulation process here, because you see that there's a normal level of stress up until time point 400, where the abnormal stress context is introduced. And you see that the stress is sensed and represented. These are the orange and the pink line. But you see also that the feeling for stress, so the amygdala activation, is quite low. And the response for stress, the green one, so the emotional response or arousal response, is also quite low or lower than the stress context itself. This is because the PFC functions to suppress it. So this is a healthy emotion regulation process. During sleep, this is even more suppressed because REM sleep comes up, that's the red line, and also restorative sleep comes up. And this helps to even suppress these feelings of stress and arousal more, and this correlates to the findings of low arousal levels during restful REMs. So here REMs is restful, and this continues every day. And at this point, the context of abnormal stress is introduced. And we see that stress does impact sleep because stress reactivity and sleep reactivity go a bit up, and feeling for stress and response to stress goes up, which is natural in an abnormal stress context. And we see that sleep still occurs, even though there's a bit of stress. but it occurs at a slightly lower level. So we see that REMS is a little bit lower than before and restorative sleep as well, but it's still present. As soon as the influence of the epigenetic processes starts to come up, this is represented by these lines. So this is the influence of the epigenetic process comes up. We see that this whole process is disturbed and restorative sleep and REMS does not come back, even though the context for sleep drive is still present. So that really means that the epigenetic influence exudes control over how stress affects sleep, because it does not come back. And even when the stress context is gone, the abnormal stress context, the person still really feels stress highly, responds to it highly. So this correlates to this anxiety-like behavior, considerable distress. And restorative sleep and REMS are not, didn't come back anymore. So this really shows the development of insomnia, because all the symptoms and characteristics are present. This persists for a longer period of time, up until time point 800, because that's the time point that the step 1's function specified for the context of therapy. We see that these lines here that represent the epigenetic processes from the higher orders go down. So the upregulated expression is reduced and the negative effects are also reduced. And we see that once these lines are completely low again, so the upregulation is completely reduced, a normal and healthy pattern resumes. So basically, we saw that the model, this is the same model, but without the context states, but we saw that the model could effectively simulate the development and persistence of ID and also the potential reversibility of ID. Therefore, I think that the findings in this thesis are relevant or quite significant, because it really showed the potential of computational models, specifically the approach introduced by Zerr. It integrated factors from different fields, so biology, environmental factors, and mental factors. And I think that the approach is really appropriate for this, because it also allows for adaptivity in these different processes. And also shows the potential for modeling sleep-related and stress-related disorders, and showing the interplay between emotion regulation processes and sleep-wake regulation processes. Of course, there are some opportunities for enhancement in future research, because the thesis had to rely on some simplifying assumptions, specifically for assumptions related to the epigenetic reversibility and the underlying mechanisms. This was mostly based on one study, the Sun study I mentioned. And this study was based on animal models. So to generalize it to humans is a bit difficult. And also, this model does not include adaptivity for other network characteristics, such as aggregation and timing. But in a realistic setting, when you integrate environmental factors, biological factors, and mental factors, these types of adaptivity normally would occur. So it would be great to also include that in the model. And to look at other genes that were found in research that could be interesting in ID as well. And also to model how exactly ID affects other psychiatric disorders and other diseases. And I hope to maybe do that in a later stadium as well. For now, I think I mentioned everything. So I want to thank you for your attention. And if you have any questions, I'll try to answer them.